To finish this section on circles, we'll look at circle theorems. Circle theorems are facts about circles that hold for all circles. And these theorems are often about angles of shapes that are drawn inside of a circle. Let's start with Thales' circle theorem. So suppose I take a diameter of the circle, call it AB, and I have another point on the circumference, call it C, and consider the triangle ABC. We can prove that the angle at C is always a right angle. And this is how we do it. We draw in a key radius line, the line connecting the center to the point C. What this does is it produces two isosceles triangles, OAC and OBC. Isosceles triangles are great for finding angles because we know that not only are two of the side lengths the same, but the two corresponding angles will be the same. So suppose I label this angle at A alpha, then I know the angle at C over here is alpha. I then know that this angle is 180 minus 2 alpha because angles in a triangle sum to 180. I then know that this is 2 alpha because angles over a line sum to 180. I know that angles 2 alpha OCB and OBC sum to 180. And I know that angles OCB and OBC are equal. So if I call this angle X, then I have X plus 2 alpha is 180. And so 2x is 180 minus 2 alpha. And so x is 90 minus alpha. So this angle here in particular is 90 minus alpha. But this means that angle ACB is alpha plus 90 minus alpha, which is 90 degrees. So we have a right angle at C as desired. We can use a very similar proof method to prove the inscribed angle theorem. Consider a quadrilateral with corners at A, B, C, and O, where A, B, C are on the circumference of the circle and O is the center of the circle. Once again, let's draw on a radius line connecting O and A. Now we have two isosceles triangles, so we can go angle tracing again. What we're going to prove is that the angle COB is twice the angle CAB. This is sometimes phrased as saying the angle at the origin is twice the angle at the circumference. Okay, so let's suppose that this is alpha, then this is alpha, and this is 180 minus 2 alpha. And let's suppose that this angle here is beta. Then same reasoning. Now, angles in a circle like this add to 360. So we have 360 minus this, which gives 2 alpha plus 2 beta. But now notice that angle CAB is alpha plus beta, and angle COB is 2 lots of alpha plus beta, therefore proving the inscribed angle theorem. The remaining theorems I'm just going to state. On the left, we have a theorem about a cyclic quadrilateral. A cyclic quadrilateral is a quadrilateral whose corners are all on the circumference of a circle. And the theorem says that opposite angles in a cyclic quadrilateral sum to 180. So if this is alpha, then this must be 180 minus alpha. Likewise, if this is beta, then this is 180 minus beta. The theorem on the right is saying that angles in the same segment are equal. This one we can actually prove quite quickly. I'll show how. If we consider these two lines here, then we use the inscribed angle theorem on each of these, giving this angle at the center as being 2 alpha. Then we can sort of go from this to this to this, thus proving that these two angles are indeed the same. Next, we have an alternating segment theorem. So if I've got a tangent line here, and then the triangle drawn as such, and this angle here, alpha, equals the opposite angle in the triangle over here. And finally, we have a circle theorem about congruent triangles. Suppose I have a point A, and the two tangents from A to the circle touch at P and Q respectively. As we know, they form right angles. But since APO and AQO are right-angled triangles, both having the same side length, OP and OQ, which are radii lines, it follows that APO and AQO are congruent triangles. That is to say, they have the same side lengths and the same angles. As a particular consequence of this, AP is the same length as AQ. And moreover, this angle here, alpha, is the same as this angle here. This angle here is the same as this angle here. You could think of this entire diagram as being symmetric over the line OA. Really, these two triangles are just reflections of each other in that line. A quick example, let's work out the size of each angle marked with a letter, giving reasons for our answers. Now, notice that we have two parallel lines here, so we can also use some earlier techniques from GCSE, like the alternating angle idea. So this means that we sort of a Z angle here means that J is equal to 53. And then we know from the alternating segment theorem that I is also equal to 53. Because we have this angle and I is opposite in the triangle. And so since the angles in a triangle sum to 180, it follows that K is 180 minus 53 minus 53. It's 180 minus 106, 72 degrees. Furthermore, it follows that the triangle is isosceles. One more example to finish. Again, we've got to find the unknown angles. There's quite a lot going on here, but we can try and just extract the key shapes. So seem to be quadrilaterals going around, so let's isolate this quadrilateral here. It's a cyclic quadrilateral, so it means that H, being opposite 94, is going to be 180 minus 94. It's going to be 86 degrees. But there's another cyclic quadrilateral hiding in here. It's this one. So this means that F is also equal to 86. And in fact, there was another way we could have obtained this. Consider this shape in here. F and H are angles in the same segment, so they must be equal to each other. And finally, we have angle G, which is just going to be 180 minus F. No special circle theorem there. Which actually just means it equals 94. That'll conclude this video and this section on coordinate geometry.